All right, let's start talking about these functions. So hopefully we started to see some pretty good graphs that would give us strong evidence, or good tables as well. Don't forget, if you can find a pattern, you can write an equation, and hopefully a lot of us start to see that. Especially, this is why we studied equivalent equations early on, because we brought this up. The base plus the height has to be what every time? 50. So what is an equivalent equation so that I know what the height is?
50 minus.
Right? I use my properties of equality to create, and I create a 0 here, create an equivalent equation. So now when I look at my height, I literally just have to type in equals 50 minus the base. Done, right? It very quickly gives me every single one of those instead of having to struggle with doing this. And it does it 100% accurately for me because it's doing the calculations. How are we calculating area? So I can go, and don't forget you can also look at it here. You hit your variable instead of typing it out. Base times, go back and hit variable, height. And it gives me every single data point there. Which a lot of us did it this way. And we very quickly see, and I know a lot of us were miffed at the question number 2, but we wanted to look at this more heavily. What is the evidence, right, that 625 or 25 by 25 gives us the biggest area? Well, early on, we see that the area is what? Increasing. And then what's it doing? Decreasing, right? So if it increases and decreases, it's going to hit a peak. Or Grayson used the correct word, and there we go, the maximum, right? Although I want to show you this, right? We see evidence that this is the maximum, but could it be something in here that is, in fact, the maximum? No, I'm saying, sorry, in between, right? So something between these points. Could there potentially be something that is a maximum? Yes. Have we collected the evidence to prove that there is not? No. So, why is it not letting me do one? DJ, can you show us our table, or your table? So what did DJ go by? Ones. So scroll down for us a little bit. And slow down one more time. So notice, does he have a little bit more evidence that that 625 is in fact the biggest area possible? Yes. You see that difference right there? Okay. So we need to recognize that there's a little bit more evidence when we go by ones. I told y'all to go by fives to speed things up, but we see that idea in the table that this is increasing, or that it hits a maximum there. Now I do want to point this out because there was some confusion about this in a second. But have we ever seen a function that is going to increase and then decrease like that?
Well, we found the button.
Okay, we can find the button. We'll talk about that in a second. But remember, linear functions either increased or they decreased. That was it. If we talk about an exponential function, it either what? It increases, multiplying by something, like a 2 or a 3. But if you multiply by like a 1/3, what's it going to do? And so it could look like this. Exponential and linear only increase or only decrease. There is no increasing and then decreasing.
You called that a word.
Which one?
The curve one.
The new curve or or this curve?
That curve.
This is, yeah, it's literally just an exponential curve.
No, that one.
Oh, that one over there? Yeah, we're going to talk about that one in just a second.
What was the button?
So, what type of function are we looking at here?
Quadratic.
A quadratic function. How do you know?
Because that's what the button said with the roof.
Okay. There's another reason. Cameron, why did you know eventually when we talked about it why it's quadratic?
Yeah, you told me.
No, I referenced you to look where?
Oh, you told me what
In the
it
book,
was. You told me in the top.
Look at the top of the sheet. What does it say at the top of the sheet near Gold Rush?
Quadratic.
Quadratic functions. It sure does. I'm not trying to trick you. I'm not trying to make it hard. Like I told you, these are quadratic functions. If you look back at the objectives, We need to define the rate of change of a quadratic function.
Okay, but we didn't know we were
There
gonna
it
use that.
goes.
Hey,
I didn't even know.
We figured it out.
But what type of function is it?
Smart.
It's a quadratic, right? Like, if you're only going to use linear regression if it's linear, you can use exponential if it's exponential. It's quadratic. We're going to look at that in just a second. I'll pull yours up, Jada.
I'm not gonna, I never seen that in the calculator.
I
Cause I wasn't
was
looking for
in
it. I ain't know one that they could do it.
It's
Right.
the same thing, you can use it all.
But it's no different. As long as you know the type of function, you can do a quadratic regression. We're going to look at that in a second. But the bigger thing is quadratic function. Now, I need you to go to number 3, or the whole class notes, because what was the first objective that we have to complete? We need what? To define the rate of change, okay? We gotta know what the rate of change is. I'm gonna come back to yours in a second, TJ, because there is important information in this one that we would miss. Okay, so Jada had hers. Jada, can you go back? Actually, I'm gonna use yours for the graph in a second. Who went by 5? Y'all did? So I'll put cameras up there. Yeah. Too bad. Alright, so Jada, can you go up to where the base was 0 for us really quickly?
Is that mine?
No.
Or Cameron, not Jada, sorry. Cameron, can you go up to where the base was 0? Okay, so let's look at the area. First off, I'll go ahead and tell you, there's definitely not any multiplication here. Do you know how I know? With 0 times anything? 0. So could I multiply by anything to go to 225? No, not even the slightest, right? So what could I do to 0 to get to 225? Add 225, right? I'm actually going to write it right here just so I can put more of it on the same space. So I've got my base, I've got my area. I'm going to use base for now. You can use height as well, but I want to look at this one. So a base of 5, an area of 225, I added 225. So for a base of 10, the area was 400. How much did I add? Not 225.
You had it.
175.
I added 175. 15. We have the area of 525. So I added 125. An area or a base of 20, I believe it was 600. How much did I add? Before I go any further, does anyone see a pattern?
It's going down like
It's going down by 50. What's going down by 50? So this would be known as, it's called okay, really quickly as a reminder, don't forget a linear function has an additive rate of change called a slope, but it can also be called a common difference.
Don't worry about it.
Huh? We talked about that on Friday. We didn't talk about it today, but we did talk about it Friday. So this is known as the first differences here. Because what is 225 minus 0? 225. What's 400 minus 225? 175. See how that's a set of differences in there, right? And so we have our first differences, and what would the second differences be?
225 minus 170.
Backwards. 175 minus 225, which would be negative 50. And then another negative 50. And then another negative 50. So what would 75 minus 50 be? Plus 25. And 25 did give us an area of 625, didn't it? And that pattern keeps going. Notice, what is the second set of differences every single time? It's minus 50. Okay? So, what notes do you think we should make to ourselves here about quadratic functions based on the table? Gentlemen, you need to have that table drawn.
Constant rate of change, but they're able to go down.
Where's the constant rate of change though? Is it the first set of differences?
And the minus, we'll both say, yeah.
And the second set of differences. So, as seen in the table, or let's say in a tabular representation,
My mom's gonna see me write that, she's gonna be like,
Why do you, like, what's tabular?
super simple, table,
well, yeah.
just
but
the
like-
adjective form.
Like the fact of me using that word for no reason.
Alright, as seen in a tabular representation, the second differences have a constant, how might we describe that rate of change? Constant what?
Rates.
It is subtraction, but could it possibly be addition at sometimes? And remember, subtraction is just adding a negative. So it'd be a constant additive rate of change. Huh. The second differences have a constant additive rate of change.
By second differences, you're talking about the box A, or do you mean the second
The second differences.
to not,
The second differences, right? You got your first set of differences here. You got your second set of differences here. You can have third differences.
Oh, wow. Fourth,
You can have fourth.
fifth.
It depends on the type of function. Okay?
That sounds
Oh, yeah, do
Yes, ma'am. No. So as seen in a tabular representation, the second differences have a constant additive rate of change. I feel like we've talked about a constant additive rate of change, haven't we?
Morning.
What type of function had a constant additive rate of change?
a linear function.
A linear function. Wait, so what? How could we describe these first set of differences then?
Linear.
We want to notice that a quadratic function has a linear additive rate of change. That might sound odd, but that is important to notice. The second set of differences is constant additive, so this first set right here is what? These are linear. Okay? So the rate of change, and we find that rate of change in the first differences. So the rate of change is linear.
So when you mean, when I say like it has a constant rate of change, that means the same thing as linear.
Nope. Remember, the second differences were constant additive, which is what made the first differences linear. If you were to graph these right here, it would create a line.
Yeah, this one.
But did this create a line?
Yes.
I'm sure it would.
They're all going up,
No.
No, it wouldn't.
No, it would not. That's the whole point. Remember, the area is what type of function? Quadratic. So it's important to notice that this function, the original function, is quadratic. The first set of differences is linear, and the second set of differences is constant. I'm going to come back to that in a second though, Grayson, to address the question you asked about how many sets of differences we can have, because it makes a lot of sense once you start looking at the equation. Okay? Please understand again though, and highlight this, box this, everything this. This is not saying that the function is linear, this is saying that the what?
Rate of change.
Rate of change, the first set of differences, is linear. The rate of change is linear, not the function itself. The rate of change is linear, not the function itself. And you can very clearly see that when we graph this data. Okay. We can very clearly see this when we graph this data. Is that data linear? Not even in the slightest, okay? Jada, can you click on the graph that you have really quickly and delete it?
So I wrote that equation down. Did we need that for anything?
Click on
We'll talk about it in a second.
You said so the rate of change is linear, not the.
What do you?
So can you click on the graph, or on the regression equation, regression function, and delete it? We can get back to that in a second. There you go. Yeah, the rate of change, right? The first differences are linear. And that's what we can see right here. The rate of change is linear. The second differences is that constant. Okay, so once again, one of the first things that we saw in the table was that the area first did what?
Got up.
So it increased is what we would say, and then it started to
Decrease.
decrease. What do we see in the graph?
Increase, decrease.
We see an increase and a decrease.
Quadratic.
Okay, I would make a note to yourself. I might even draw a quick little sketch and make the note to yourself that we graph this in the calculator. But I would make the note of, hey, we have our base, we have our area, and draw that quick sketch in there. And in the graph, we also see the function increase and then decrease.
How do we know where to put like base and area and height or whatever? Like I always get confused which line to put on. Because it'll make a different equation, which will.
Correct. The y-axis, y is dependent. The area depends on the base. The area also depends on the height. So you could put base or height here. It does not matter.
So if I have height and base,
Well, if you have height and base, neither of them depend on the other really. It'll actually just create a linear function.
so if I had like,
The whole point is that we're trying to study the area though.
so on the stairs when we did, and it was like your speed, and then it was like your height, so I would.
Well, no, it was the time and your power. And
Okay,
your
so-
power depended on the time.
What? I thought your time would depend on your power,
No.
because the more power you had, the faster you.
But you had more power because you went faster. Just like you had more power depending on whatever your height
Okay,
was.
so your height would be the
Independent.
independent, and then your.
The area is always dependent in this case, okay? So, in the graph, we also see that the function increases and then decreases. Does anyone remember, well, there is another detail I do want us to see in this graph. Does anyone see anything where that it might jump out to us about the graph that we haven't seen in other functions?
Oh,
Anyone see it now? Say it again. Yes, there's another detail I want you to see about quadratic functions though. There we go, that's the word, right? They're the same on either side, so they are what? There is symmetry. Quadratics have symmetry about, and mathematicians got really original here, they call it the axis of, any guesses? Symmetry. So we want to pay attention to that term, that axis of symmetry. And so remember, this is all based on the graph section, but does anyone know what that peak or that maximum is called in a quadratic? Not a mathematical term. It starts with a V. It goes through the,
Vertex.
there it is. The vertex. The vertex is that key point. It's either the highest or the lowest point of a quadratic. Okay? It goes through, we have that axis of symmetry that goes through the vertex.
Why is independent in axis? Why is independent in axis?
Because it is.
No, I'm asking is X is independent.
Yes. Yes.
Wait,
Someone have a question?
it says quadratic have symmetry about the axis of symmetry.
And the axis of symmetry goes through the vertex.
So
See how it goes
they
through that
have
vertex right
symmetry.
there?
I don't like the word about. It
I don't
doesn't make,
either.
it doesn't make sense to me.
Well, you have symmetry about a line of symmetry.
Oh, okay.
You always have symmetry about some line of symmetry. That's just,
Yeah, I
Oh,
just
The
read
language
that.
that we use.
The line has.
yes. Well, the quadratic functions, it's not a line, right? But the quadratics graphically have symmetry about this line or about this axis of symmetry.
Okay.
Okay? And so we want to make a note that this is a vertex, is the maximum when the graph is concave down. I have not introduced that term, but this graph is what we would say is concave down. Okay?
Concave up is gonna be the other.
Yeah. The way that my high school, I want to say calculus teacher, helped us remember the difference between concave down and concave up is that concave down is like a frown. Literally, concave down is like a frown.
Well, it
Okay.
goes down, yeah, but I say, I don't know if I
Yep.
can remember that one.
It helped me, right? So concave down is like a frown. Notice the vertex is a maximum. In the other direction, it's concave up, like a cup, is what she used to tell us. So it's concave up, and notice the vertex in this case is a what? So vertex is a minimum. There is some key language in this lesson that you need to make sure that you understand and know, right? And again, you would have that axis of symmetry through that vertex. Yep, concave up is like a cup. Last couple of quick notes. All right, Jada, talk us through it. How are we going to get the equation for this set of information? So, linear regression? So, what's the first thing you're going to hit?
Menu,
So, hit that menu.
and then
We're going to analyze it.
and go to regression.
And we still want regressions, but I want you to notice what type of function are we looking at? See how there's all these other types of functions? Click on that quadratic. And there it is. So y is equal to, and it has it as -1 times x squared plus 50x plus 0. You can also just rewrite that as just -x squared plus 50x. Right? That's our equation. What do you notice about this equation that's different than all the rest? The highest exponent is a what? A 2, right? Quadratic functions have a highest power of 2. Hey Grayson, what was the set of differences where it started to become constant? Do you remember? Did you write it down? You didn't write it down, this is going to be a problematic time. But look at your table. Where did the, what set of differences did it start to be the second? Second differences. Wait, what's the highest power here? A 2. So any guesses what set of differences we would go to if it was x cubed? If it was x to the 5th, what set of differences would you have to go to? Yep, that's literally what it is, okay? So if you look back at it, right? Right, so we are looking here, it's not constant yet, but at that second set of differences, It is constant. Notice this is x to the second because it's quadratic. So this would be x to the first because it's linear, and then it's just constant. Okay? We all good with that idea? Any questions about that? So I need you to make sure that you use this lesson to complete those objectives that we talked about at the very beginning, right? From this task, we should know what rate of change defines a quadratic function. I'm not going to make you write an equation for that rate of change, but you need to know that a quadratic has what rate of change? What type of rate of change is this? The first set of difference is linear. Remember, constant, linear, quadratic. We need to know what quadratic functions appear in tabular, graphical, and algebraic representations. And then notice, can we use a calculator to write the equation? Yes. There's some other things that we're going to learn about it. In fact, not the next lesson, but the lesson after that. So sorry we didn't get to volume 1 today. We'll definitely get to it tomorrow. That's all we'll be working out of. The lesson after that is all about learning how to write the different equations, because there are multiple equations for quadratics, but we can still use calculators to help us. Yes, KJ?
Did you write the test?
I am almost done. I will have them done by tonight, and give them back to y'all tomorrow.
As of now, do you know the lowest grade?
No. I will never make you. Hey, I forgot to ask, or collect, but if you have any homework to turn in that is late, I need that. Did you last Friday? Okay. I don't remember. Please leave the textbook if you had to borrow
Remember, I
one.
came after us and did some of it in here with me. Just making sure you remember, because I don't.
Mr. Kenny,
Yeah.
do I still have to come in during enrichment to do the test?
You don't have